Buenos dias. Every action has an equal and opposite reaction. So here are a few things that spring to mind, right? Let's have a look at them. An aeroplane. Why does an aeroplane go that way? Is it every action has an equal and opposite reaction? What we have is low pressure and fairly cold air going into the intake of the turbine and everything of the jet engine, right? And it heats up and spins and the fuel mixes and then and what we have is low pressure and high pressure. You get thrust. Low pressure and high pressure. So that's not really every action has an equal and opposite reaction, is it? Balloon. Every action has an equal and opposite reaction. But there, nothing's happening. So the balloon all of a sudden has high pressure here and a shrinking pressure at the front, which moves the balloon forward. So it's high pressure coming out, and the balloon runs away. So it's hardly every action has an equal and opposite reaction, is it? Every action has an equal and opposite reaction. It's a bit tricky, isn't it? So that one, it's pressure differential causes the thrust. Low pressure at the front, goes through a sequence of events and comes out as high pressure. Creates thrust, the wings and the atmosphere, the flaps come down and create lift. Up she goes. A helicopter, the shape of the blades, the rotors, right, they're shaped not like that, but they're shaped. So turn, they create lift. So they go like that. And exactly the same as the flaps on a plane, they create lift. Atmosphere. Try a helicopter on the moon. No, senor. It will not move. It will not go anywhere. Parachute. Guy jumps out of the helicopter. That was convenient. And as soon as he jumps out, he can literally pull the cord. And the little mini chute goes up, catches the atmosphere, then pulls the main chute. Atmosphere. If this guy jumped in a vacuum, hasta la vista, baby, he could be holding a rolly cigarette paper as he was falling, and it wouldn't even move. It wouldn't even move because there is no resistance. He could scream as he's going down. Paper wouldn't move and you couldn't hear him. So you'd ignore him. You're right. Bye. There is no resistance in a vacuum. Let's leave the Saturn V until the end. A jump jet. a Harrier. So you have the thrust coming down, right? That thrust that is coming down is reacting with the atmosphere, and it creates a resistance. The higher up a Harrier is, the less efficient that downforce would be. And then when it comes into land, it comes all the way down here, and yeah, that thrust, it creates a cushion, and that cushion is felt there. Right? So now, the Saturn rocket, you see it go up, and you think every action has an equal and opposite reaction. Right? Looks like it, doesn't it? Up she goes. But you'll notice that all of the thrusters are slightly, not underground, but they're in a kind of a, I don't know, a container, not a container, but it's built up and they're inside a built up area. That thrust is insane, right? And the way the bottom of the Saturn V is shaped, what happens? They bang on the thrust and this just goes mental down here. And it comes. And what's happening is it is the pressure coming down and bouncing off of the bottom and coming back up that lifts the rocket up. Its own thrust comes down, hits all of this area and creates a blast up, and it slowly climbs, slowly gathers speed, and then when it's here, it's cleared the bottom area, and it's still, you can see, right? And then you've got this blue that comes down. That will be reacting first onto this, and it is lifting the rocket. So it's hardly every action has an equal and opposite reaction, is it? Really? It's a bit more, it's not just out it goes and up she goes. Let's look at a thruster a little bit closer up. Okay? So there's, 5 of them, I think, on a Saturn V. Is that why it's called a Saturn V? So here we are, we're looking at one thruster, zoomed in. So what's happening? This is where it's coming out, right? Now let's talk every action has an equal and opposite reaction. You've got the thrust coming out of here. Why is that going to go up? You've got the thrust pouring out of this nozzle, like, why? Where is this push coming from? I'm being deadly serious. You've got this thrust coming out. Why are you going to get an up force here? Every action has an equal and opposite reaction. Thrust comes down, so why? Like, it just goes up, it's just a thing because of Newton's third from the 1600s. That's what you're saying. That's it. Anytime I ever mention thrust in a vacuum, the scientific definition, the explanation is, no, Newton's third. Every action has an equal and opposite reaction. That's it. It's not really enough, is it? Considering that it was in the 1600s. 1600s. Right? 1600s. We're now in No, let's go to 1969. 1969. 1600s. 1700s. That's a century. 1800s. That's 2 centuries. That's 200 years so far, right? 1900s. Hang on a minute. That's 300 years. 1969. Arguably 350 years. So Newton, 350 years. When were the Wright brothers? When did they take off? Was it 1902 or something? Why on earth have people related every action has an equal and opposite reaction? Because of what Newton allegedly came up with in the 1600s. Same as Roma, isn't it? Was it 1676? Electricity came into play in Europe in 1880. I mean, 204 years before there was electricity. It came up with a theory, well, the Io and Jupiter thing, right? Aye. Anyway, back to this. Why? Just because there's thrust coming out, it's coming down. What on earth is creating an uplift? Why? The reason it goes up, because in the atmosphere, it creates chaos. And the pressure builds up. And that pressure build-up is what pushes against the pressure build-up. It's resistance because there is atmosphere. There is resistance because there is atmosphere, right? That is what makes it go up. It isn't a case of, oh, that's going down, so the rocket must go up. Science, please. Oh, Newton's third. Every action has an equal and opposite. Okay. No. Aircraft, when they fly, right, they all have different ceilings. They all have different heights that they can go to. But all of the passenger planes and that, I think it's 40,000 or 42,000. Average is 36, 37, depends on the climate, depends on turbulence, depends on the plane to a certain degree. But I think 42,000 is the maximum for some, or they can all, look, I don't know 100%, but some of them go a little bit higher. And the reason that they do fly so high is because the higher they are, the more efficient the thrust is. Slightly thinner air, you get a better mixing of fuel to air for the thrust, low pressure, high, it all works. But you can go too high. So some planes, let's say the safe ceiling, let's say, I don't know, it is 42, right? That is prime altitude. Certain planes, if they go to 50, all of a sudden, the air is too thin. And they lose that perfect air to fuel thrust mix. And the thrust, all of a sudden, be a little bit knocky and lift. It's too high, the air is too thin, the thrust drops, and you start to get a bit of the lift doesn't work. All of a sudden, you are too high, and you cannot go any higher. If you went any higher, your engines would stall. if they stalled and you're at that altitude, you could have a lot of trouble restarting those engines. And the lift, you lose that lift because it's too thin. Now, this is just 50, 60,000 feet. There are some Air Force jets like the Lockheed and that stuff that can, I don't know what their ceilings are, but they are like the sports cars of the sky, and they can go up higher. But everything has a limit. Now, the reason the rockets go up is because they do not rely on lift. They don't rely on that kind of a thrust. They've got their own mixture, right? Like the solid rocket boosters, and they have their own mixture. Bang, it ignites. Chaos, a big thrust bubble pushes the rocket up. Once it started to go up, you get this, its own little cloud resistance is going up with it. And it pushes and it pushes and it pushes. Now, I have to be careful here because this is where we say gravity, isn't it? And like it has to, the thrust obviously has to overpower Earth's gravitational pull if it's round, etc., etc. I'm kind of serious, right? Flat, round, who knows? One thing is for sure, thrust in a vacuum. Once you are in the vacuum of space, and there is no atmosphere at all. Now for me, the rocket goes up, it goes through the clouds, or it's, people watch it go up and it's out of sight. And it's gone, that was so cool. That's when the movie starts. That is when the movie starts. Because they haven't been to the moon. I know they haven't been to the moon. They know they haven't been to the moon. Lots of people know. There's lots of reasons why they haven't been to the moon. And thrust in a vacuum should be universal. People should just know there is no resistance in a vacuum. So when they say that a spacecraft creates its own resistance and then bounces off of it, that's highly logical, especially when it weighs quite a few tons. Right, here we are. Come on, thrust. Atmosphere. Up she goes, right? You clear the atmosphere, and you're in the total vacuum of space. You're coming down because you've had a great trip. You have flown up, done your Earth, couple of orbits of Earth to make sure all the systems are go, build some speed up and stuff, whatever it is they do. On the way, just as they leave Earth, right, there is this maneuver. Fascinating. So the command capsule, the Eagle and stuff comes out, right? I don't know who did it. Thrust out, get to about here, This is in front of the rocket, traveling at between 20,000 and 24,000 something miles an hour. Okay, and somebody jumps in and goes, moves forward. They do a 180 and then somehow go back or something. And then the eagle is facing that way or something. Anyway, look. It's Disneyland up there, isn't it? It's Disneyland. We still, oh yeah, because luckily we'll still see. Don't have to do it on the board again. But here we are. We've done all the stuff, all the good stuff. The moon. We can see the moon. We separate from the command capsule. Right? Poor Michael Collins looking out the window. Hey guys. And there they are in that thing called the Eagle. It's not the, come on. It's not the prettiest of spaceships, is it? Right? And it's got all the gold trim, isn't it? Love the gold trim. All the. I always thought there would have been more, like some dust on it. But it was pristine, wasn't it, when it landed? It's amazing. And you could, where they landed, you thought there would just be dust everywhere. But there wasn't. It was quite tidy, really, wasn't it? It's got stuff up here, whatever, look. Alright? Yeah. All good. A little antenna there. Now, the moon's down here. We were 60 miles up. 60 miles up. And we were travelling at approximately 6,000 kilometres per hour. And we are going to come down here and land on the moon, aren't we? Piece of cake. That's the ascent stage and the descent stage together. 26, 27 tons. Now, there is no resistance whatsoever in a vacuum. So, all of a sudden, we find ourselves now, there is no resistance, right? So why do we think that when it goes like this, that it's going to build pressure up under here, enough pressure that it's going to be able to do like the Saturn V and slow 26, 27 tons down, travelling at this speed. So we're hoping that it goes the Eagle has landed, but in reality it would go because there is no resistance. There is nothing for any of the thrust to build up against. This is not a case of every action has an equal and opposite reaction. All of the other examples you saw, there is a reason for the opposite reaction, whether it be a pressure differential or atmosphere or building up its own bubble because of the atmosphere. But up here, there is nothing. There is nothing for the thrust to build up on, to then create an updraft and push or slow the Eagle down. You cannot use thrust in a vacuum, self-propelling with the two magnets. What is happening is they cannot use the vacuum. Sound doesn't travel in a vacuum. It's basically no molecules, no particles, no atoms. There's one. There is not enough for 26, 27 tons to slow down with thrust in a vacuum. There is nothing. It is not going to build up any pressure after the rocket. It's just going to go. They cannot interact with the vacuum. The glass jar, sealed. So what is being said is somehow every action has an equal and opposite reaction, that the thrust is coming out and somehow it's just pushing against the bottom of the spacecraft. But how? How? It doesn't matter what shape you make the thrusters. It doesn't matter what shape or how big or how long they are, because there is a speed bump. And that speed bump is the vacuum. So it doesn't matter what you try to do. Every time that thrust comes out of here, it's just going to go, and it will never be able to build up. It's a physical impossibility. It's a lie. Thrust cannot work in a vacuum. Where would they have learnt how to fly in a vacuum, land in a vacuum, and in 1/6 of Earth's gravitational pull? Where? I was asked this question. Oh, they had simulators. Oh, really? It's crazy. It really is. It's an insult to people's intelligence. The gun. People say that, don't they? Yeah, what if you fired a gun in a vacuum? I'll give you that one. Not this one, because there's no recoil. .12-gauge shotgun. If you had a 12-gauge shotgun in a vacuum on the moon, right, and you were holding it like this, and you could gently press that trigger, bang. It's an explosion. It's not thrust. There is a massive difference. It's an explosion. There is only one way that force can go, and it's going to go that way. The round, the explosive, it's a barrier, isn't it? It goes bang. Yes, I reckon that the shotgun would just go, and it would just carry on forever. But thrust isn't a random explosion, right? It's totally different. So yeah, you can have that one, but even if you had 1,000 12-gauge shotguns lined up and you let one off every 1/10 of a second, bang, 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 it's not going to slow 26 or 27 tons down, traveling at 6,000 kilometers an hour. It's illogical. Look, it didn't happen. It didn't happen. Chuck, right? This is probably one of the prime reasons why it didn't happen. And this little thing that you guys love, well, Newton's third, every action has an equal and opposite reaction. That's how thrust in a vacuum works. It doesn't wash. There needs to be a little bit more than that. Some bit more physics, proper physics, pressure, speed, thrust, not a vacuum, because in a vacuum, nobody can hear you scream in a vacuum. Nobody can hear you scream in space. Nobody can hear you do anything. You could fart in a vacuum next to somebody and you could fart again. They maybe feel the vibrations, not even the vibrations apparently. There is no resistance in a vacuum. So you cannot use thrust in a vacuum, unfortunately. Am I a scientist? No. Or a physicist? No. Am I qualified in any way? Depends how you look at it, right? There is no resistance in a vacuum. All of the other examples, it is not just a case of Newton's third. They all have pressure, atmosphere, lift. None of that is available up there. If it's not a dome. I have to say it. I'm objective. I am objective enough that it doesn't matter what other people say, I'm quite happy to say, listen, who knows, right? To be objective and to be able to hold two thoughts, two different theories in your mind at the same time is a gift, because it allows you to chop and change when the evidence and the facts keep coming. And I tell you what, those facts and that evidence just keeps on coming. Coin flip. All right, folks. Now, I haven't read this yet. Gracias, Tari. I'm going to have a look at this today. I've had a good scan, but not properly. Live. 16 pages of fantastic colour. The spacewalk. Look at the date. Oh yeah. So I'm going to have a look at that today. And is he really? Astronaut White floats over Lower California. But is he? Is he really floating over Lower California? So many years after, it will be interesting to see what is said. Okay, folks. Just being objective, okay? Just being objective. It's not smart to hold on to this stuff as new evidence is dug up from places. All right, laters.